So we're going to work with work today. From physics, the definition of work is force times distance. And I was always a little unhappy with that definition, and I tried to demonstrate my unhappiness by sharing with my students a little joke, or not a little joke, but playing a little joke on my students. That is, I would ask one of them to hold the book out at arm's length. And most of you probably have electronic copies of the book, so let me just share with you. I don't know if you heard that earth-shattering boom of me putting the book down, but it's a huge book. If you get the whole thing, it weighs a good 8 pounds. So it's not something you really want to put in your backpack unless you're going to need it. And then I have somebody hold it straight out to their side, and after a little while, you know, it's not easy to hold it straight out to your side because it's kind of heavy. Imagine taking an 8-pound weight and holding it straight out. And then I would joke that, well, hey, what's the problem? You're not doing any work, because work is force times distance. That's the definition from physics. You know, I'm not going to argue with physics. I'm a mathematician, but it always left me feeling a little uncomfortable. In any case, we're going to look at Hooke's law as applied in calculus. And it tells us the force required to maintain a spring stretched x units beyond its normal length is given by this little equation here. F of x is k times x. Now, if you're playing around with your email, you should have gotten an email from me earlier with regard to some problems. So to help you keep up if you have that email. But let's take a look at this first one. Now this Hooke here is Robert Hooke, who actually played an instrumental part in history simply by being part of a little wager between himself, Christopher Wren, and Edmund Halley. And that little wager led to the publication of Principia by Newton and literally changed the world. But that's a different topic for a different time. For now, let's see here. I think I want this one. So this is the one we're going to start with. Let me make that a little bit bigger here. There we go. So a force of 16 pounds is required to hold a stretched spring 2 inches beyond its natural length. How much work is done in stretching it from its natural length to 5 inches beyond its natural length? Well, a couple things to take care of here. The first of which is the fact that we're not given things in feet. In the English system of measure, typically we work with feet and pounds, not pounds and inches. So let's see. Let's take down a few notes here. We got a force of 16 pounds. So, oops, right here. So we got F equals 16 pounds, and that stretches it 2 inches. So the first thing I want to do is I want to convert that to feet. So how many feet in 1 inch, or what's the relationship between feet and inches? Someone help me out there? Feel free to Google it if you need to.
12 inches is 1 foot.
Perfect. So let's put 1 foot in the numerator because that's the units I want, and 12 inches here because that's the unit that I want to cancel. So, all right, looking good there. Now, the nice thing here is that you're really multiplying by 1 because 1 foot is 12 inches. And we know multiplying by 1 doesn't change anything, but I am going to switch units. I'm going to get rid of inches, and I'll have 2 over 12 feet. Or basically 1/6 of a foot. Okay, so that's nice. Robert Hooke's law tells us that f of x is some constant times x. And in this case, we've got f of x, well, f of 1/6. So f of 1/6, k times 1/6. That force required to stretch the spring, 2 inches is 16 pounds. So 16 equals 1/6 times k. How would you solve for k? Let's multiply both sides by the reciprocal, which is multiplying both sides by 6. 6 times 16 is 96. So great. Now we've got the value of k. So we can be a little bit more specific than what this is here. We know that for us, f of x equals 96 times, oops, that should be an x, not a k. Beautiful. Now we need to figure out how much work is done in stretching that spring up to 5 inches. So let's go back here, 5 inches. I want to convert that to feet. So I'll do the same thing here that I did just a minute ago. I'm going to multiply by 1 foot is 12 inches. The units are going to cancel, and you're left with 5/12. And a lot of times, instead of writing foot ft, you can just put a little dash like that. I mean, kind of the drawback there is that it looks like other things, like maybe a derivative or units of minutes from trigonometry. But in this case, it's feet. Okay. So we want to add up all the work done in stretching this spring from 0 feet to 5/12 of a foot. So that's going to be done by integration, 0 to 5/12 of 96x dx. So you're adding up all the work that's done incrementally to pull it out farther and farther until you get to the endpoint. So that's going to be 48x squared between 0 and 5/12. And if you put in 5/12 and square it and clean it all up, what we'll end up with is 25/3 for our answer. And I'm just going to help you out with the units here. In the English system of units, work is measured, anyone? In foot-pounds. So 25/3 of a foot-pound. And you can see your force times distance right here. So there'll be appropriate units for the units of work. So there's your first example. How are we looking with that first one?
I'm wondering what you did up toward the top left. When you put one under that. Yeah, I didn't understand this step.
Okay, so
the 1/6, like f is 1/6 equals k.
Sure. So let's go back and take a quick look at the problem here. So right here, let me see if I can underline it or highlight it for us. Right here tells us a force of 16 pounds is required to hold a spring stretched 2 inches. So that 2 inches is 1/6 of a foot. So coming back to our expression here, if I put in 1/6 for x, f of 1/6, well, the problem gave me that was 16 pounds. So you're okay with the left-hand side of this?
Right, yeah.
All right. And for the right-hand side, I just put in the 1/6 for x. Now, I don't know what the constant is, but 1/6 times k had to equal 16. And I just solved for k.
Okay.
That didn't sound like a very convinced okay.
It was just confusing why they're all equal to each other.
Okay. All right. But are you comfortable with that, though?
Yes.
Okay. Thank you. I appreciate the questions. Thank you. Anything else on this one? All right. Let's try another one. And that next one is here. It says, suppose 5 joules of work is needed to stretch a spring from its natural length to 26 centimeters, or natural length of 26 centimeters to 39 centimeters. How much work is needed to stretch the spring from 30 centimeters to 35 centimeters, rounded 2 decimal places? All right, so this one's different. And it's a little bit of a pain in the following sense. You've got units of centimeters. And kind of like our last problem, where we converted inches to a bigger unit of feet, what do you think we're going to have to convert to this time?
Centimeters to inches, and then inches.
Yeah, centimeters to meters. So it's kind of annoying. Now, we get a little bit of a break on part of it because 26 centimeters is the natural length. So that's kind of like the zero part, zero starting point. But yeah, we still are going to have to do a little conversion. So let's take a look at that. We'll start with 26 centimeters. And I want to convert that to meters. Well, the good thing about centimeters to meters is that it's really just moving the decimal. So it's 0.26 meters. And what was the other one? It was 39 centimeters? Yeah. So 39 centimeters. Anyone? That'd be 0.39 meters. Okay, so those are a couple tiny things to get us rolling here. It says 5 joules of work is done or is needed to stretch a spring from its natural length to 26 centimeters to 39 centimeters. Well, we're kind of back where we were in the first place with our previous problem. I know that the force required here is a constant times x. That comes from Hooke's law. But I don't know how much work is done. They do give me some information that's going to allow me to solve for k. Actually, I do know how much work is done, 5 joules. So let's see. We're going to integrate k times x dx from its resting point to its stretched point. Now for us, let's call the resting point 0. How much farther am I going to move if I move to 0.39 meters? How far have I moved from here to here?
0.13.
Good, 0.13. So let's put that 13 up here. Now this represents the work done in stretching that spring from 26 centimeters to 39 centimeters. How much did they say we were doing in terms of work? What was the number that they gave us?
5 joules.
Good, 5 joules, perfect. So that's equal to 5. And this should allow us to solve for k. So that's going to be 5 times k times x squared over 2 between 0 and 0.13. And that's going to allow us to get an expression to solve for k. So let's see here. Let me do it this way. I'll leave the 5 halves and the k out in front, and then I'll have 0.13 squared minus 0 squared. And that's going to equal our 5 joules. And let's just keep it over here. 5 equals that. So this is just a little linear equation. We can solve it and get the value of k. So this cleans up a little bit. That's going to be 5 equals 5 halves times k times 0.169. To solve for k, I'd multiply both sides by the reciprocal. So let's see here. Trying to think if there's a quick way to do this. Nah, it just looks kind of ugly. So it's going to be 10 equals 5k times 0.169. Something's bothering me here.
Oh, wait, I have a question.
Oh, you know what? I shouldn't have that 5 there. Was that your question?
Yeah, that's what I was going to ask.
I was looking at that going, something doesn't work right here. I think I borrowed the 5 from right there. So it should be a 1. There we go, a little Photoshop. That's looking a little bit better. Actually, I don't even need that, right? And just get rid of it. So if you divide both sides by 0.169, what we'll end up with is 100,000 over 169 equals k. So not necessarily the most pretty constant in the world, but you know, it'll work. That works for us. Okay. Yeah, let's see. If we figured out the units, what would they be? That'd be joules divided by meters squared. So joules divided by meters squared would be the units here. But I'm not going to try and keep track of the units because it's just going to be a big headache. It's actually a really good idea to do so, because if you can keep track of the units, it helps you make sense of the problem and let you know if you got a mistake. But it just gets really cumbersome. It would slow us down. So, but thanks for asking. Let's see. The second part of the problem asks us to define how much work is being done to move from 30 centimeters to 35 centimeters. So let's see about that. Now 30 centimeters, how far beyond the natural length is 30 centimeters?
4.
4 centimeters, good. So what we're going to do is take our function, which is f of x is 100,000 over 169 times x. And we're going to integrate that function from 4 centimeters up to, let's see, what was 35? 35 would be 9 centimeters past our natural length. So 0.09, and that's 100,000, 169x dx. All right. All right, so 100,000 over 169 times 1/2 x squared between 0.04 and 0.09. Kind of messy, but eventually what you can get is 25 over 13. And the units that will be left, because meters squared is going to cancel out with the meters squared on our constant, the units that will be left will be joules. And I'm not going to make you become an expert on all these different units of measure, but you should be able to get this number. And if you rounded that to 2 decimal places, as required by the problem, it'd be about 1.92 joules.
In the chat, we were talking about how it should be 10,000
10,000?
over 169.
You know, I was bothered by that a little bit. Let me just see if, let's see, 10,000. Let's see, where's, oh, that's my calculator. So I'm not sure that I disagree with you. 10,000 divided by 169. Let's just take a look. Math 9, arrow between 0.04 and 0.09 of x dx. Five over 26. Something's wrong. Yeah, so thank you, Matthew. Yeah, so I forgot there's a 0.0169 here, making that 0.0169 there. When we saw we do get 100,000 over 169 equals K. And with all that, we end up with 25 over 13 would be our final answer for the integral. And that gives us 1.92 joules. So that matches what we're supposed to have. I'm feeling better about that one. Thanks again, Matthew. All right. So, okay, a little bit different here. The one big difference between this problem and the last problem, and one thing that I want you to note about these things overall, is that this law talks about the force required to maintain. It means once you pull it out, to hold that spring in place requires a certain amount of force. And the force required to hold it in place is given by this law. Now, when you're moving it in and out, the amount of work done, the amount of force needed is going to vary. The amount of force that you need is going to vary as you move it from left to right or up and down. But if you're just going to hold it in one spot, then that force you require is going to be some constant times the distance that you're stretching things. So that's a little bit of a subtle difference between the first one and the second problem here. There is a part B on this one. It's not so bad. So before I move on to part B, are we okay with part A? Part B is just going to be about one line. Before I move on to part B, anything else on part A? Let's move to part B. How far beyond its natural length of 10 newtons, or beyond its natural length will a force of 10 newtons keep the spring stretched? So, okay. Let's take a look back at things. We know that f of x, well, we actually now have a constant here. F of x is 100,000 over 169x. So we're going to apply a force of 10 newtons to that. Let's see if we can't keep it in place. So how far will that force stretch the spring? Well, all you got to do here is solve for x. So I'd multiply both sides of this equation. The 10 newtons equals this by the reciprocal here, which should be 169 over 100,000. That times this gives me 1,690 over 100,000. You can cancel out the zeros if you want. 169 over 10,000 equals x. So that would be in meters. It's about be 2 decimal places, 0.069 or 0.001. Let's see. 1, 2, 3, 4, 5. 169. 1, 2, 3, 4, 5. Yeah. That many meters, which would be about 1.7 centimeters if you convert back to centimeters. Now, one thing that I find annoying is that WebAssign sometimes a little inconsistent. If you look at what they ask they want it rounded to 1 decimal place, which is what I did. But you know, in the first one they wanted 2, the second one they want 1. I find that a little annoying. I'll try and be a little bit more consistent with you guys. Cool. How are we looking on that one? Part B here. You okay with part A and part B?
I'm kind of confused on what exactly do K and X stand for?
So X is the distance beyond its natural length that you're stretching things. So let me see if I've got it in my notes someplace back here. So we'll go here. This is the force required to stretch the spring X units beyond its natural length. So if you have some kind of a spring, and when you hang it, it's maybe 10 centimeters long, you want to stretch it to 20 centimeters, you're stretching it 10 centimeters beyond its normal length or its natural length. So X is that distance, how far beyond its natural length you're stretching it. And then F of X is the force required to stretch it that far. So does that help out?
What is K then?
K is a constant. It's going to depend on the particular problem. So this is a general rule, but when you're looking at a particular spring, you're going to have to find out the exact value for K for that spring. And that's going to vary from problem to problem, from springs in a clock to the suspension coils in your car. Those kind of things are all going to have their own special value of K. And you have to solve for that value of K, you know, depending on the particular problem. So we did that here with this first example. We said, okay, in this problem, 16 pounds of force will stretch the spring 2 inches. Now 2 inches has to be 1/6 of a foot, but these two pieces of information allowed me to solve for that constant. So for this particular problem, K was 96. Now in the problem we just finished, K was rather ugly, 100,000 over 169. So, but that's just the constant for this particular problem. And you're gonna have to solve for K in pretty much all of these problems that you do. Does that help out? Feeling better about those?
Yeah.
Okay, thank you.
Will we do more examples like this?
No, that's the last one. Sorry. We're gonna have to move on to some different examples. But let me tell you, this one down here, that's a tough one. I actually avoided that one in your homework because as I was prepping this lecture, I went through that one. It was a good 15 or so minutes work, even for me. I'm like, we don't need to be that mean to our students here. So we'll kind of skip that one. But I mean, these problems do get a little bit more challenging. I did try and keep it reasonable for us though. Okay.
How long do you think the homework should take us?
That's a good question. It's going to vary by individual. It's going to depend on, just how familiar you are with some of the stuff. I mean, the good news for you in looking at this 8th edition of the book for Calc 2, it's been a couple of years since I've taught Calc 2 out of this book. They've changed editions. They've removed a lot of hard physics topics. Centroid, center of mass, fluid pressure, fluid force. These were some really challenging physics problems. The only physics problems left that I can see are in this section. So yeah, this one's going to be a bit of a workout. That's why I'm going to spend the first, almost half of the class on this one section. And then we're going to have to motor through section 7.1 and 7.2. All right?
Okay.
All right. So let's suppose that this is a rather big fish tank. And of course, being that it's a fish tank, it's filled with water. And we're going to see about pumping the water out of the top. And our goal is to, first of all, empty the tank halfway. Empty the tank halfway. So that'll be our part A. And then empty the tank completely. Now, even though there's possible room for error and interpretation, I just kind of, decided to use units of feet as just a little hash here. One thing that we're going to have to know in terms of problems like this is the density of water. There's a couple figures that you'll see here. The one that I'm used to is 62.4 as the density of water. And that's going to be, let me see if I can write it right here. So that's going to be rho. It's not a P, even though it looks like a P. It's a Greek letter, rho, is 62.4, and that's going to be pounds per cubic foot. So that's the density of water. And that's going to become an important part of this problem. I think the book currently uses 62.5. I don't know. Maybe there's more pollution in our water nowadays. I don't know what happened there. But so our goal is to take the water in this tank and pump it out the top. And the top edge of this is 4 feet high. So we're just going to clear the top edge is what's going to go on. And we want to figure out how much work is done in pumping all the water out, at least down to the halfway level. So let's keep in mind that work is force times distance. And I'm going to start by figuring out the force first. How much force do I have to use to move a slice of water? Now I'm going to give this coordinates of 0 and 0 down here. and that's going to move up, or this is going to go all the way up here. If this is a distance of 4, can somebody tell me the coordinates up top here?
0, 4.
0, 4. Thank you. 0, 4. So let's keep track of that. Now I've drawn a slice through this region, kind of like what we did with area and volume problems. We're going to start by calculating what happens to just one little slice here. Anyone want to suggest what the thickness of this slice is? What have we used for the thickness of our slice in chapter 6?
dx or dy.
Dx or dy? Yeah, since this is a horizontal slice, that'd be a dy slice. All right. Now really, if you take the density times the volume, that's going to leave you with units of force. The volume of this is pretty simple. If you take a look at the slice through this box, the volume is just going to be the area of that slice times its thickness. So it's going to be rho. How am I going to calculate the area of a slice? It's really kind of like the top of the box there. What's that area going to be?
48.
Yeah, 48. 6 times 8 times the thickness, which is dy. Perfect. So overall, 48 times rho times dy. So that's the force to move that one slice of water. But now we got to figure out the distance that we move it. Distance. Well, the distance is going to be the top minus the bottom. And I don't know exactly where that is. So let me put some coordinates here. Can someone suggest some coordinates? What would be the x coordinate of this general point right here?
0.
0. And so since we don't know what the y coordinate is, call that 0 and y. So the distance that this has to move is going to be top minus bottom, which is going to be 4 minus y. So how much work is done moving that one slice? So moving that one slice, the work done is going to be, well, actually I don't want to put the integral there yet. So the work done to move one slice work equals force times distance. So that's going to be 48 times rho times dy times 4 minus y. Oops. Got off the screen there. My bad. I can rearrange that. Let's write it this way. 48 times rho times 4 minus y dy. Okay. That's the work done moving one slice. So let's turn our attentions to part A. I want to empty the tank halfway. So if I'm going to empty the tank halfway, what's the lowest value of y that I should look at if I'm emptying the tank halfway?
2.
2. So from 2 up to the top, which would be 4. All right. So we'll integrate from 2 to 4. Let's see, I'll put the 48 times rho out in front of 4 minus y dy. Yay. Okay. Do we need to show all the antiderivatives and stuff like that? We good there? Okay. So it's going to be, let's see. 48 times, let's put in row, 62.4. Where'd my calculator go? $48 times 62.4. Yeah. So 2,995.2. 2,995.2.
What is the density?
I'm using 62.4 pounds per cubic foot.
Right. That's for water.
That's for kind of like tap water. The book's going to use a slightly different figure of 62.5. If you're dealing with seawater, seawater is actually less dense. They have a density of about 62 pounds per cubic foot. But the value that you're supposed to use for the density will be given to you by the problem. It's not trivia that I expect you to know.
Okay.
All right. And let's see here. That's going to be times what here? I don't feel like doing this out. 2 to 4 of 4y minus y squared over 2. So 2995.2 times would be 16 minus 8, which would be 8. And putting in a 2, I get 8 minus 2, which would be 6. So multiply that by 2, you'll get, what, 5,990.4. And the units would be foot-pounds. Yay. All right. These problems are kind of intense. So if I went too fast through some portion of it, let me know. Be happy to go back and help you look at this a little bit more.
Professor,
Yeah, please.
how did you get the 2 when you're doing the integral 2 to 4? How did you get the 2?
Ah, great question. So for part A here, let me be clear that we're doing part A. We want to empty half the tank. So half the tank means the values of y are going to come from 2 to 4. They're going to come in this range. So that's where we got the limits from, is realizing that we're emptying just half the tank. Does that help?
If you do to 0, would you get the same answer?
If I put in a 0, 0 to 2?
Yeah, 0, 2.
I don't think so. Let me take a look here.
Because wouldn't that be half the tank as well?
Well, yeah, but see, the difference is it's the bottom half, and there's a lot more work done in the bottom half, because if you imagine what happens at this bottom slice, you've got to move that a whole 4 feet to get to the top. And that's a lot more than you're moving, say, this bottom slice, which is only 2 feet. So if you just did 0 to 2, if you emptied this portion of the tank, then my guess is it'd be a lot more work. In fact, there's a part B here that asks us to completely empty the tank. So what do you think we'd have to integrate to completely empty the tank? How would that change my limits?
Would it be, your limits would be 0 and 4, correct?
Perfect. So if we did 0 to 4, let's just kind of crank that out. So it'd be let's just use this 48p, which is 2,995.2 times integral from 0 to 4 of 4y, or excuse me, 4 minus y. I'm thinking we're going to get something much bigger. There's much more work done towards the bottom. So it'd be 2,995.2 times 0 to 4, 4y minus y squared over 2. So plugging in a 4 here, I would get 16 minus 8. So it'd be 8 times that. So 8 times 2,995.2. So yeah, that's a significant increase in terms of the amount of work here. So what, that's just a little bit below 24,000. So punch that into a calculator, 23,961.6 foot-pounds. So yeah, actually a lot more work getting that last little bit there. Cool, good questions.
I'm sorry. Can you just explain to me how you got right above B in the brackets 8 minus 6? Can you explain that?
Sure, if you put in the upper limit into this function, 4 times 4 is 16. If you put in the upper limit to this part, I get 16 over 2 is 8. 16 minus 8 is 8. And then I did the same thing with the 2. 4 times 2 is 8. 2 squared over 2 is 4 over 2, which is 2. 8 minus 2 is 6. So just by plugging in the limits, I got each of those values. And of course, the difference is 2, so you double that, and we got our answer. Okay, appreciate the question.
Just to follow up with the someone else just said a little bit earlier, if we did 0 to 2, would it make a difference? I just solved for that, and it would have been like 6 times more, if you will.
Yeah, that makes sense. That makes perfect sense, because this was 8 times more. So yeah, the difference, yeah, it would be really the work in doing the top half. So yeah, that makes perfect sense. Thank you. Appreciate that. And again, the reason there is a difference is because moving these bottom layers requires you to move a much bigger distance than moving the top layers. So, I mean, just imagine if somebody asked you to bring in some stuff from the baseball diamond, and you had a choice of bringing something in from right field or from first base. First base is a lot closer than way out in right field. So you'd be doing less work by doing the stuff nearby. All right, all the questions are great. Is there anything else on this one? Okay, tell you what, let me pause things here.